induced electric field. So basically, my dear students, we know that EMF is generated by, EMF is nothing but the work done by electric field. The EMF of anything is nothing but integral of, EMF is integral of E dot dl. This is the definition of EMF. It is the work done by electric field. It is the energy transferred by electric field. But when we talk about the conservative, when we talk about here, it is a work done by electric field in a closed loop. But if you can recall, electrostatic field was a conservative force and work done by it in any closed path must be 0. Yes, but in this case the electric field induced is not conservative, it is a non-conservative electric field. So that's why work done in a closed path will not be 0, rather it will be equal to the EMF induced, that is d phi by dt. So we are going to write something about these points. This electric field is induced electric field, induced electric field. It is not same as the other electric field. It is not conservative. It is non-conservative. Non-conservative. Second thing which we would like to add here is it forms closed loop lines. Closed loops. And it doesn't terminate or originate at charge. So this is a unique electric field which is a non-conservative in nature and it does not terminate or originate at the charge. So basically we can also determine its value. Suppose we have a loop where there is a uniform magnetic field present in the loop and this magnetic field is changing this is a time varying magnetic field, B. So dB by dt, time varying magnetic field. So if this magnetic field vary with time, then of course EMF will be induced in this region, and due to that EMF the concentric electrostatic field lines will be generated. Concentric electrostatic electric field lines will be generated not just within the loop but also outside the loop. Not just within the loop but also outside the loop. So these lines represent the electric field lines. These lines represent the circular induced electric field lines, induced non-conservative electric field lines, electric field lines. So you can see these are also concentric in nature, these are concentric electric field lines, and also it's a symmetric about this variation in magnetic field. We can determine the values of electric field as well, because electric field lines represent the direction and magnitude of electric field. So we can do so by assuming, let's say for any point outside the electric field will be like this E. So everywhere you can see E into 2 pi r, E dot dl will become E dot dl. This can be written as E dot dl can become E is uniform integral of dl into cos 0 for the complete loop. So it will become E times dl, integration of dl in the complete loop of radius r will become E times 2 pi r. Okay. So this is first equation. Further, using Faraday's law, you can also write EMF as d phi by dt. using Faraday's law, this EMF is nothing but d phi by dt. Now in this case, if you can see, the flux can be written as magnetic field into area. Area is constant, only magnetic field is changing. So this will become d phi by dt will become area will become pi times r square. Remember, we have to write the area of only the region in which the flux is present, not the complete area. So let's say the radius of this area where the flux is present is capital R. So pi r square times dB by dt will become your EMF. Let's say this is equation number of 2. So if we equate these two equations, we can write this electric field as, so by equating these two equations, you can clearly see we have E into 2 pi r, E into 2 pi small r will be equal to pi r square into dB by dt, pi r square times dB by dt. Just manipulation. You have to understand what we are doing. We are opening this Faraday's law. E in E dot dl, that is the definition of EMF, can be written as E into 2 pi r along this circular loop, and E from Faraday's law is d phi by dt, that is area into dB by dt. And just equating this, we can calculate that electric field will be equal to r square by 2r times dB by dt. This question was asked in your previous year exam. So just basic understanding will help you to solve this. Now there is slight small variation. This is the electric field for outside points. Outside points means this is true for r greater than r. What about inside points? So if you talk about the inside point, then only one thing will change. If you talk about any point inside, let's say this is small r. For this, if you want to calculate the electric field over there, value of electric field, then my dear student, only what you have to do is the area which you are in this equation, when you write the d phi by dt, you are taking the complete area pi r square. But for the electric field inside, you have to only consider the area which is inside this periphery, because we are calculating the EMF only for the inside points. So then your equation becomes E into 2 pi small r, no change on the left hand side, will be equal to, on right hand side we will write only pi times small r square, that's all, into dB by dt. So we will be having this pi gets cancelled out and this 1 of the r also gets cancelled out, and the electric field, induced electric field inside the loop will become r by 2 times dB by dt. So this is the result. Either you can remember the values or you can remember the method by which we have calculated it. So this is the induced EMF, concept of induced EMF inside the loop and outside the loop. So now let us solve few problems based on our understanding of these concepts. Let me revise again. What was the first concept? The first concept was Faraday's law, and due to which we have calculated the change in flux. Second was the Lenz law, which gave us the direction of EMF induced, and third was the induced electric field, in which we have determined the value of induced electric field, which is a non-conservative concentric lines, by using the definition of potential, that is work done by electric field in a loop.